Alrighty, let's see here. Alrighty, so yesterday we were talking about, I guess we did our introduction to nuclear chemistry, where we were talking about decay processes that things go through. We saw some kind of rough estimates of how we can figure out which type of decay a particular nucleus will undergo. We're going to see some of them will need multiple decay processes. Processes. There we go. To become stable. One of these most common ones is uranium-238. Uranium-238 is kind of our heaviest naturally occurring natural nucleus that we'll find. So uranium is found in various rocks and that sort of thing that it can that is naturally occurring. So it is there, and it's got a really long half-life. We'll talk about half-life in a bit, but it's still here from when it was first kind of created in the Big Bang type, after all the elements kind of figured out what they're doing. Um, so with this, it's still around, and it is decaying. We're going to see that it eventually stops at lead 206, and there's quite a few processes that need to occur here. Lead has an atomic number of, let's see here, 82. So overall, we're going to be going through quite a few processes. I mean, at minimum here, just to get to that atomic number, we would have at least 5 alpha decays going on. But we're going to see there's a lot of different things that happen here. This is called a decay series. And there are only 3 that we know of. So we have 2 isotopes of uranium and 1 of thorium that do decay. And so this is just one example of one of them. But through this, we can see we're going to have a ton of different processes that happen. The first one is an alpha decay, which means we're going to get 23490, which is thorium. And this will undergo 2 beta decays afterwards. Beta decay, of course, 0 minus 1 beta. Remember, the purpose of beta decay is to increase our atomic number. What is between thorium and uranium? I don't remember. PA. What the hell is PA? Protactinium? No. I have to look this because I don't remember what PA is. Oh no, I don't remember at all. PPP. What the heck is PA? Oh, praseodymium. No, that's PR. What is protactinium? Who knew? I would have thought that would be. Oh no, platinum is PT. Anyways, we have our protactinium there. Now that one undergoes another beta decay. (92). Now we're at uranium 92 or uranium 234, which is going to go through some. By the way, all this is, I'm just going to just show you not only the length of this, but also we're going to encounter that radon problem again as we go through this. So now we're going to go back to do a couple of alpha decays. We get now back to thorium. This particular thorium is now happy to degrade as is. We get 22688, which is radium. Radium, of course, which killed Marie Curie after she discovered it. By the way, there's an interesting documentary on Netflix. It's not really a documentary. What am I saying? It's a historical kind of fake documentary that talks about the use of radium back in the early America. I don't know what it would have been, 30s maybe, somewhere around there, 20s or 30s, and how everyone was like, "Oh, radium is so good for you," and all this fun stuff, and so they used to paint watch dials with radium so that you could see them at night. The radium absorbs the energy and you can see it glowing at night. And so radium was kind of all over the place. And so these girls that would be painting the watch faces would be ingesting the radium as they go, because they would be licking the paintbrushes to apply the radium paint onto the things. And so there was all sorts of horrible disasters, and it's interesting. I liked it. So it's called Radium Girls. But anyways, this one is the one that decays into our dear friend Radon. Oh no. Let's keep going though. More alpha decay. What do we got for radon is polonium. Polonium is 2. This will be 218. Polonium is 84. After the polonium, we do our second to last alpha decay. This one gives us lead. And this one it'll be lead 214. But that's not the lead we're going to stop with. Yes, Radium Girls. Oh, is it the Radium Girls? So, even so. I liked it. It was cool to see just how messed up politics make things. It's yet another movie of, people ignoring science. And so, go figure. We now have a couple of beta decays. Too many neutrons, so we go through beta decay. So we're going to 214, 83, bismuth. Another base. See, notice how crazy long this decay series is just to get for uranium to decay into a stable nucleus. So all of these nuclei thus far are unstable. So it's got to go really, really far to go all the way down to lead. So now we can do an alpha decay again. So we're going to see this one's going to be 42 alpha plus 210, 82 lead. But we still have 2 more to go because lead 210 is also unstable. So lead 210 will go through some beta decay processes. Back to bismuth. Bismuth 210 unstable. Beta decay. Polonium again, and then finally our last decay. Uh, 206 lead. We did it, and that one happens to be stable. So lead 206 is stable. But look at how many reactions we've had to go through to get there. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 decays in order to get to where we need it to be. So uranium has a long way to go. Thorium and another isotope of uranium will also undergo decay series that are just nastily long like these are, and so you end up with these. Now, of course, this is where the radon problem is. Of all of these other elements, they're all solids. But this guy is a gas, which means if there are cracks or holes or something in your rock that's allowing it to come out, radon can come out, and look, it's going to go in decay and it's going to spit out alpha particles. While normally alpha particles we're going to see are not that dangerous from the outside of our bodies because they're pretty big, they're going to be halted by our skin. Unfortunately, radon being a gas means we can inhale it, and if a radium nucleus decays while it's inside of us, then it can spit out the alpha particle inside us, which can be very damaging to tissues. So it's a problem. But we'll get to that when we talk about radiation exposure. Again, radon is going to be kind of our most, where we get most of our radium or radiation from in the natural world is from radon. So it's a noble gas, it's unreactive. We're going to see that reactivity has nothing to do with nuclear processes. So even if we put radon into other compounds or something, it will still spit out its radiation at us. So, anyways, the point is we get 13 steps to get us there, betas and alphas, and we end up with finally our stable nucleus there. So we end up with our lead. And so it's interesting that we can use uranium, therefore, to actually we can use lead to date. Mr. Relax. We can use lead to date things because lead-206 is not otherwise occurring naturally in large amounts. We know the ratio of lead-206 to lead-208, I think, is the most common lead isotope. If we end up seeing an excess of lead-206, that tells us where uranium has been. Or if there is uranium there, we can see, okay, well, with this amount of lead-206, we know that there was this much uranium at some point before all of these happened. And so we can have an estimate of how old something is by using uranium dating. You've probably heard of carbon dating before, but that's only, maybe up to 50,000 years can we use carbon dating. Uranium dating can go billions of years. So we've estimated the age of the planet by using uranium dating. But that's a little bit ahead of us. So we're good there. Okay, so there's our decay processes. They're naturally occurring. They're releasing alphas or betas or positrons, or they're capturing electrons. These are normal ways that unstable nuclei will kind of fix themselves. All right, but we can induce nuclear processes too. We can create isotopes. Oftentimes we'll do this by throwing neutrons or protons at things and hoping that they will accept them. So for example, we can take some nitrogen, very common nitrogen for us. We can throw at it a helium. We can use various things to get this helium to be sped up. We end up getting out a oxygen and a proton. And so we can. This is a helium nucleus, by the way. It's not an actual atom of helium. We're just looking at nuclei, right? So it's an alpha particle. This can be generated by alpha decay. We can use a radioactive material as a source of alpha particles. So if, for example, we happen to have our uranium-238, look, we can get it to spit out alpha particles. Or we could take any one of these other nuclei that we see in the uranium-234, or whatever we're looking at, uh, we can have it release these alpha particles and we can use them. So with those alpha particles, they are positively charged, so we can accelerate them using various electric fields. We can get them to smash into a nitrogen atom, and in doing so, create oxygen 17, which is not a common isotope of oxygen. Right, we know oxygen typically is 16, and we can get a proton out as well. And so we can kind of make isotopes through this means. So we can throw alpha particles, we can throw neutrons, we can throw protons at nuclei to get them to change, to transmute. And so we can generate new elements this way. This is a process of nuclear transmutation, where we can take elements into new elements. So we can do this to force us to get interesting isotopes. So if we wanted to label something with a particular isotope, or we needed a particular isotope for medicinal purposes, specifically for medicinal purposes, this is very useful. You can generate them kind of where you need them using this kind of process of transmutation, and you can then administer them to the patient before they decay. And so you can kind of do these normally. Let's see what some good examples of those. We can also create all those other elements beyond uranium this way by throwing protons, neutrons, and alpha particles at them. What was the example I was going to look for? I thought I saw one in the book somewhere. Well, whatever. I guess I don't have an example of a good isotope that this would make. Maybe something with fluorine. Fluorine, as we saw with PET scans yesterday, or iodine, common ones that are used in medicine. You can throw nuclei at them. We can also take our uranium, throw a proton at it, or rather a neutron, which I'm putting upside down. And we can, no, a proton. Yeah. Let's throw a proton at it. Is plutonium next, or is it neptunium? It is neptunium, okay. We can make elements that don't naturally exist by throwing particles at them. So while neptunium-239 I don't think is very stable, we can do this. We can make new elements. And same with plutonium and all of the rest of the actinides, as well as all those elements past them, the 7p block there. None of those elements naturally exist. We can make them, we can make individual atoms of them that exist for fractions of a second, but we can make them. So a lot of these things are, we don't ever really deal with them because they don't exist normally, so they don't really have uses for us, and they're also terribly unstable, so they're going to decay. So, but it's still cool to be able to make new elements, right? So we have elements all the way through 118 oganesson, which is pretty cool. So even though that's, almost 30 above what naturally occurs in terms of atomic number, we have quite a few synthetic elements, which are pretty interesting. We're going to see that neptunium through oganesson, but their atomic numbers there are called transuranium elements. So beyond uranium, we can make them in labs, and that's kind of it. And often these would be named after places that they're made, or scientists who have made them. So you've got like nihonium, which is Nihon is the Japanese word for Japan. You have Moscovium, which is Moscow. You have Oganesson, which is named after Yuri Oganessian. who is the scientist who was able to come up with this. You have tennessine for Tennessee. Neptunium is, of course, after the planet Neptune. So, we have all these other stuff. A lot of them are named after scientists and places. Berkelium, Einsteinium, Nobelium, Mendelevium. All those are synthetic elements, so just named to honor people. All right, so that's kind of stuff we can do with those. Um, Back to stability, while I had kind of gone off on this, yeah, Californium is there, Lawrencium, or Livermorium, I don't remember. Uh, they're all named after that sort of thing. So, um, that's okay. That's all right. It's one of our last lectures. Who cares? So, let's talk about stability again. So we saw we had this kind of nice proton to neutron or neutron to proton ratios that we saw. We saw the p to n ratio goes from 1 to 1.5 or so up to element 83. That means good things. We're going to see that even numbers tend to be more stable. If you have even numbers of protons or neutrons, you tend to be more stable. It's interesting, and I think your book has a pretty cool diagram of just elements with odd atomic numbers tending to have 2 or fewer stable isotopes, but elements with even atomic numbers have more than 2 stable isotopes. And so there's just something special about having even numbers of protons there. And we're going to see the same case for neutrons. These tend to be more stable. There are only 5 nuclei in existence that have both an odd number of protons and an odd number of neutrons. So it's not common to see that. So deuterium is one of those where we have an odd number of protons, 1, and an odd number of neutrons, 1, to make 2,1 hydrogen, which is deuterium. There are only 5 nuclei like that exist. Not very many, where we have hundreds of ones with even numbers of both, and about 50 or so of ones that have odd numbers of protons, even numbers of neutrons, or vice versa. So even numbers of both tends to be more stable. We also see that there are magic numbers of protons or neutrons. 2, 8, 20. Okay, I need to look these up. 28, 50, or 82, yeah. So your lucky lotto numbers, if you are a nucleon, are the following. Those just tend to be very stable numbers. So lead, for example, has 82 protons. That's a particularly stable number. And if it has 126 neutrons, that's lead 208 that you get out, which is very, very stable. Let's see, what else do we have here? This, of course, is oxygen. This is helium for proton-wise, but neutron numbers like these are good, typically. So there's, of course, an exception in that this guy, tritium, is terribly unstable. This is an exception to that rule, even though it's got an even number of neutrons, and that number happens to be 2. This is still an unstable one, just because if you think the neutron to proton ratio here is 2. So that's really, really high. So this is going to definitely decay for us. So we still want to kind of have our neutron to proton ratios following that between 1 and 1.5 idea. So these are not guaranteed to make anything stable, just like having even numbers, that doesn't make anything guaranteed to be stable either. But these are just kind of trends that we see. So those things tend to make you a little bit more stable. All right, let's see. I'm not going to talk about cyclotrons and synchrotrons here. That's particle physics that's mostly dealt with, but they're essentially just machines that are capable of accelerating nuclei to smash into each other. Particle accelerators, they're called, um, where you can, our Hadron Colliders, there's all sorts of fun terms there, where you can take nuclei and accelerate them using magnetic fields or electric fields to force them to get to super high speeds to crash into things. So you can do that. But that's not something that we need to worry about. So, cool. Let's see. What do I want to talk about next? Oh, let's talk about Half-Life. So Half-Life is particularly interesting for radioactivity and nuclear chemistry because it is, of course, a first order kinetics process where your T half-life or T half is the amount of time for half of your sample to react or decay. And it's going to be a constant. It's going to follow typical first order kinetics. If we remember first order kinetics, that's a terrible way of doing it, but there we go. That's also terrible. I'll get this right one day. There we go, that's better. If we start here at 100 grams, and then 50 grams, then 25 grams, these should all take, pretending here, but these should all take the same amount of time to decay. So to get rid of that first 50 grams takes your half-life. To go from 50 to 25 takes your second half-life, the same amount of time it took to go from 100 to 50, you go from 50 to 25. And then to 12.5 would be another half-life, and so on and so forth, 6.25 after that. You would have that mass of your amount left. So your T half would be, let me do it in this special T. We've talked about this in kinetics, of course. Do we remember the formula for first order kinetics? Of course not. Remember, for first order kinetics, we have the natural log of A at time t was kt plus ln AO, if I remember correctly. It's been a while since I've looked at kinetics too, so forgive me if I'm wrong. Let's double check the book here. Do I have this right? I think so. And so if we substitute it for 1 and half respectively, we end up getting 0.693 over your half-life will be your rate constant. So you can figure out stuff based off of that. Typically, though, when we talk about radioactive decay, we make things easy. We say something has a half-life is 80 years. After 240 years, how much of a 30-gram sample remains? And so if you really wanted, you could calculate K for this and plug it in and you would be able to get your answer. Or you can just use it mathematically. Well, 840 is going to be 3 half-lives. Rather, 240 is 3 half-lives. So we have, we have 1/2 cubed. We're doing 3 half-lives, so we have 3 halves there. We do this, and we get 30 over 8, which is going to be 3 point something. 3.2 Thank you. Oh, 7.5. Of course, it's easier. That'd be how much you'd be left. See, your internet's not laggy. It worked out just fine. And so you can do it this way. Or if you really don't want to use exponents at all, you can just do 30 divided by 2 equals 15, divided by 2 equals 7.5, divided by 2 equals 3.75. There you go. That's 3 half-lives. That's 1, 2, 3. 3 half-lives get us to where we need to be. So calculations for this tend to be pretty easy for nuclear chemistry. But again, if you really wanted, you could take your half-life, plug it in here, calculate K. Once you have K, you can say, okay, K times 240 plus natural log of 30. And you could figure out the natural log of your substance remaining, and then if you were to solve for that, you would get 3.75. But who wants to do that? Kevin wants to do that, but the rest of us can just do normal basic math. So we can be easy about it. Okay? Half-life is pretty boring. What's interesting, though, is, well, we saw with kinetics that the identity of your compound will definitely impact, and this, all that sort of thing, and will impact how fast it reacts and all that. So you see that nitrogen in various different compounds with oxygen will react differently and at different rates. What's interesting is that nuclear decay is completely constant. Does not care about kind of how, let's try that again, what the element is doing. So if you just have uranium they both decay at the same rate. No matter what, if your uranium is solid, just pure uranium, or if it is uranium hexafluoride, or uranium 6 fluoride, I guess we should be correct with our nomenclature here. In the gas state, it doesn't matter. These will decay at the same rate. Whereas previously, we would see that UF6 as a gas would react differently than uranium solid. And we'd have all sorts of different things here. Let's just label these, by the way, just so that we're looking at the same isotope. Doesn't matter. So unfortunately, that means that while we could prevent something from reacting by binding it up in a chemical species, for example, if we don't want our iron interfering, we could throw a chelating agent on it, or you could precipitate it out as iron carbonate or something. These are ways we could get rid of things to prevent them from reacting, right? However, with nuclear chemistry, you can't do that. No matter what you do, your uranium will keep decaying. So even though the radon, you may be able to make radon with fluorine, you may be able to react it with fluorine to make it into a solid or something, it's still going to be decaying the whole time. So unfortunately, we can't stop this process. This is a constant process that is occurring regardless of how your element is behaving otherwise. So, sucks. So radon is a problem, as always. Let's see. What else do I want to talk about here? We talk about kind of the rates of decay. We have units for these that we talk about. We have the becquerel. This is named after a scientist, Henri Becquerel, who studied this stuff, who first found that these radiation can affect light. What are they called? Things that people used to film. There we go. Things people used to put in cameras to take pictures, right? They were able to see that. He was able to see that radiation would also be able to affect film, and so he was able to discover a lot of these things. And we see that this is one disintegration per second. That's what a becquerel is defined as. And so you're looking at one nucleus disintegrating per second is a becquerel. And so, of course, because it's first order kinetics, there is a dependence on concentration. So, or the amount of substance you have. So a becquerel is not a fixed unit, but you're looking at an instantaneous bit and say, okay, right now at this point, uranium is degrading at 80 million disintegrations per second. And tomorrow maybe there'll be 79.99999 disintegrations per second. But that's a unit that we deal with. Another one is the Curie, which is CI, which is a number that I don't remember, and I have it written down here, which is 3.7 times 10 to the 10 disintegrations per second. This is a Curie. And so this unit is, that's the disintegration rate of 1 gram of radium, which is what Marie Curie studied and died from and discovered, and all these fun things. Polonium too, she named polonium after her country of Poland, even though she was working in France, so she's also got francium there too. But anyways, fascinating woman, by the way. Nobel Prizes in physics and chemistry, that's pretty awesome. And I mean, sadly to say, at the time, a woman doing it even, which was phenomenal at the time. Also fascinating stuff. Oh, speaking of things that I meant to look up, actually I did look up. This is my last night reading as I was going to bed. I did look up neutron stars, Kevin, and they are fascinating in that. So neutron stars. Okay, let's go on to our tangent here. Neutron stars. So neutron stars have densities that approach the densities of nuclei. So we're looking at something like if we were to shrink the Earth to 200 cubic meters or something like that, we would end up getting the mass of a neutron star. So if we were to shrink that, we would see that's the density, rather. So the entire mass of the Earth put to 200 cubic meters, that amount, that density, would be about what a neutron star is. Or consider something like this. Something like this, like a matchbox, would be about billion tons. So that would be, I don't know, making this number up, 15? Billion is 9, trillion is 12, quadrillion, no, it's quintillion. So you'd have billions of tons of something like that, just for density. So they're incredibly dense. So almost the order of nuclei. So their densities are on the order of 10 to the 15 or so kilograms per cubic meter. So huge, huge, huge. Consider that, water is 1,000 kilograms per cubic meter. So the most dense substance that we have, elementally speaking, is roughly 20, so it's 10 to the fourth. So this is where we have lead, is somewhere around there. So consider that the density of a neutron star is way, way, way more. Now, neutron stars are interesting that they are made up almost entirely of neutrons, though they do definitely have protons there as well, and some electrons. There are regular atoms in a neutron star as well. What is interesting, though, is while nuclei are held by the strong force, that's the force that the neutrons generate to keep protons together, neutron stars, even though they're made of the same things as nuclei, are held together by gravity. So because these things are so close together, and there's so many of them, and they're so massive, gravity is actually the force that holds them together rather than the strong force. So as a result, you can get neutron to proton ratios way over 1.5 in the nuclei that you'll find in neutron stars, because they don't have to obey the same laws that we would have here on Earth, where we don't have gravity holding together nuclei. We have strong force holding together nuclei, and the strong force kind of goes off at about 1.5 to your proton to neutron to proton ratio. So with neutron stars, you can have way above that. You can have tons more neutrons per nucleus. And so you have this overwhelming amount of neutrons in the nuclei that are in your neutron star, and they're all bunched right up next to each other. So you have all this sorts of crazy stuff happening. What's also really cool is they have temperatures of like 10 to the 11 Kelvin when they're newly formed, which is incredibly hot. And just in a few years, they decay to about, or they cool off to about 10 to the 6th Kelvin. So that's a remarkable amount of heat transfer that's taking place there in just like about 3 years. I don't know, somewhere around there. It's fascinating. So these lose a ton of heat just by emitting neutrinos, which are many things. Neutrinos are 0, and there's tiny particles that can be released. Those come out, and those are the source of the radiation. What's interesting, these are also rotating incredibly quickly, 700 times a second or so. They're rotating almost at the speed of light, which is pretty crazy. If you were to like take the circumference and spread it out on a line, if you were to look linearly at that speed instead of angularly, pretty cool stuff. And so because they're spinning, yeah, they also have incredibly strong magnetic fields because of their spinning. And as they emit radiation, because they're spinning, it kind of looks like a lighthouse. So they're also called pulsars because they seem to pulse energy, but that's just because they're rotating and energy is coming off continuously. But as they rotate in certain ways, the energy is pushed off in different directions, and so you get them kind of as like lighthouses in space. It's really cool stuff. But they do stuff that we don't talk about here. And they don't really undergo the same decay processes because they're able to have much stabler nuclei at higher neutron to proton ratios because of that gravitational force. Anyways, that has nothing to do with what we're talking about. That's astronomy, that's physics, not my expertise, but it is cool, and I'm glad you had me look it up because while there was a lot on the article that I read that I had no clue what was happening, talking about these limits of solar masses and blah blah blah. It was still cool to look up. Anyways, we're tangent complete. Of course, that's not on your final. Don't you worry about neutron stars. Where were we? We talked about half-lives. Let's see. Okay, let's talk about how do we detect radiation. Yeah. So oftentimes, when we look at the three, we kind of have two main ways of looking at them. The most common one is the scintillation counter. And there's also a Geiger counter. A scintillation counter, which is the most common one, has a special kind of coating on it. So there's a detector with a coating on it. And that's going to be what's called a phosphor. A phosphor is a material that emits light when struck with a particle. And so, as you can imagine, you have your maybe your alpha particles or whatever coming in here. They're hitting this screen. That screen then flashes out light every time a particle hits it. That light, this is your phosphor, will then go to something like a photomultiplier tube or some other detector. We have many ways of detecting light, one of which being a photomultiplier tube. We can convert light photons into electrical signals. And that signal, which is often a current or a voltage, is proportional to how much light is coming through, and so you're able to see how many alpha particles are bombarding your target, your phosphor, at a particular time by looking at this. So this is kind of the most common way. So scintillation is kind of that flash of light, and these detectors work in real time, so you can see exactly how much radiation you're being exposed to by looking at collisions with that phosphor per second. You can make estimations that way. Geiger counters work a little bit differently. They have electrical components as well. You have some sort of battery here, or series of batteries. I think the one that I've used uses like 8D batteries or something, a terrible amount of energy. You end up hooking that up to a negative source here. You'll have a positive source on the other side. You have an evacuated tube, or actually it's a tube with something like argon in an inert gas. When you have argon plus your gamma ray, you can split argon into argon positive plus an electron. That argon positive migrates towards the negative, the cathode there, right? And so it'll be attracted to that, and once it hits the cathode and interacts with it, it changes the potential a little bit, which can be detected by some sort of voltmeter or something like that, and you'll be able to detect it that way. So you have radiation coming in here, your gamma rays or particles or whatever, hitting your argon gas. That argon then can move and interact with your negative cathode, and then you'll end up getting some signal out which you can detect. And oftentimes that's just an audible like sound, and so it's cool stuff. But they're less useful because these aren't quantitative as much. They're more just qualitative. Do I have radiation here? How much do I have? Is a different question. Scintillation counters, you can tell quantitatively what's happening. You can see exactly how many are happening at a given rate. But Geiger counters are more for just, is there a lot of radiation here or not? So these are kind of the handheld devices. Scintillation counters are more machines, so they're a little bit bigger, and you want them to be kind of still. You don't want to be moving them around, but these Geiger counters are handheld. So, cool. That's that. We have just a little bit left to talk about. We have energetics as well as fission and fusion that we're going to talk about, but let's talk about them next week. I think this is a good place to end for today. So next time, that's Monday, we will have energy and then fusion and fission that we'll talk about. That's it. That's all we have. So I'll go ahead and put your homework up for this as well. It will be due next Sunday. So Tuesday, so we're going to be done on Monday. So we can have potential reviews on Tuesday, Wednesday, or Thursday, depending what you want to do. So I can do one of these, two of these, all of these. I'm happy to do them. So, but it depends on how many questions I get. So you can put questions from exams, questions from homework, any of the past homework or past exams, because again, your final is going to be cumulative. I will try and put up your practice exam as well by this weekend so you can start working on that. So you can bring questions from that as well. So it just depends. So post questions kind of by Monday night or so, and we'll see kind of where we are, and I'll determine which days and how many days we'll do review sessions, and they'll be at the same time. So if you do that, we'll see how far we go. And if I decide, okay, it's just going to be Wednesday and Thursday or something, then that's what it'll be, and that'll be it. So okay, so try and post questions in Discord by Monday night that you'd like to go over, so I can have an estimate of how many we'll need for our review sessions. And I'll try and do them later so that they're more closer to the final exam. And that way you can also post more questions, then also you'll have a little bit more time. So we'll see. Alrighty. So cool. I guess we're good then. So I'll enjoy your weekend. Remember, no honors meeting tomorrow. So everyone will enjoy their weekend. I'll see you back on Monday. So enjoy.